I'd like to start by thanking David and the organizers of this meeting. When I was a postdoc in the 1982 to 85, I remember that I went to Joe and I said, okay, I wanted to work in statistical mechanics. So he would, not for the first time, he would pull out a notebook with all the list of his papers. He remembered that more or less in early 60s he did something. He would then find the paper in the notebook, and then in some file cabinet he would pull out some reprint, and this he did for in many occasions. So as you may know, he was also famous for doing some of the early methods in web propagation random media called the smoothing method, which works when the noisy part is relatively small. And we were working on a different problem, which was kind of deep philosophical problem on the origin of irreversibility and non-recurrence. So these problems went to how to derive like Boltzmann equations, things like that. And the take he did was to find simple models that by solving them mathematically you would understand some of the deep ideas involved. Well, what I'm going to talk about today is somehow related to this, but it's about using modeling, numerics and asymptotics to understand some biological process called angiogenesis, which is the growth of blood vessels out of primary blood vessel. Okay, so my collaborators are these people from my university, Vincenzo Capasso, who told us about the problems, and Bjorn Birney, whom we told about the problem and helped a little bit. Okay. Right. Okay, so this is from Mice and Men to explain what the angiogenesis is. So this is vascularization of retina. The above pictures belongs to a mouse. So this is, they are born blind, as you may know, and then from a blood vessel that is here, there are many capillaries that move around, advance and cover the retina. These are men, so the difference is that the vascularization starts about the week 16 of conception, and then there are like secondary vascularization, some vessels atrophy and disappear. In the end you get a more ordered pattern. This is a natural process that can be natural, as in these cases above, or it can be induced. So in general, what you have is some region in a tissue where the cells have a lack of oxygen, which is called hypoxia. Then what they do is they release some growth factor that arrives to some nearby vessel. Then the walls of the vessel open up and emit these capillaries, and they try to go to the region where there is lack of oxygen and nutrients, and eventually they form new capillaries, and this growth factor is consumed, no longer released, and the thing stabilizes. In pathological cases, like growth of tumors, what happens is that the same process, the tumor takes advantage of that, but it keeps releasing growth factors and eventually grows and colonizes other parts. What do you do about this? Well, the usual thing is, for instance, these are lab experiments from the lab of Elisabetta Deiana years ago. Well, they put some pellet with angiogenic factor somewhere in this cornea of a rat, and then they use their anti-angiogenic drugs and see how the angiogenic network is affected by the drugs. Of course, one would like to do this somewhat better by understanding better the process and eventually reducing it to a control problem, to how to avoid, for instance, that the vessels advance to that region. Okay, there are many models that have been proposed over the years. The field started with Judah Folkman in 1971, and he was the one that, he was a doctor in medicine, so he proposed that there was some factor that attracted blood vessels. He called that tumor angiogenic factor in the case of cancer. The early papers were using like continuum modeling, reaction diffusion equation, so on. The ones I'm going to talk about are the ones that try to reconstruct the angiogenic network. And typically the easiest ones take advantage of the fact that the cells of a vessel, the tip of the vessel is formed by highly motile cells that do not proliferate. They move by chemotaxis, for instance, in the direction of the gradient of this angiogenic growth factor. And on their stem, there are other cells that just follow them and proliferate. So the easiest models is to model the vessel as just a point particle, and the trajectory of the point particle is going to be the vessel. Okay. Then there are more detailed models in which they distinguish between the stalk and the tip cells. They go to the microscopic scale and see how the cells may move by adhesion gradients and all kinds of things. In our case, okay, so this is the simplest model that we use. We try to understand the statistical mechanics aspects of this. So this is a complicated multi-scale process. As I said, we are going to study the mesoscopic scales, millimeter size, or hours time. And the model, you have the tips of the vessel that just move as a particle led by white noise here, some chemotactic force that is proportional to the gradient of the growth factor, some friction. Then we also have other processes, because every now and then the tip branches into two, so more tips are created. And okay, so the probability of creating one is proportional to some response of the angiogenic factor times some selector of velocity. So we assume that there is a main velocity directed towards the hypoxic region, and this is a Gaussian around it. Okay? And then there is another process which is important here, which is called anastomosis. So when a tip has been moving here, creating a vessel, a new one may impinge upon this, then it forms a bridge like the one that I showed in the previous picture, and it stops. So this is like a creation of particles process. This is an annihilation process. Okay, many things like haptotaxis, motion by addition gradients, blood circulation, vessel pruning, and other processes we ignore in this model. So this is like the early stage angiogenesis. From this, our take was to derive a deterministic equation for the density of these active tips. So we counted how many of these tips were active at a given time t, and try to derive a equation for the density of that we could then analyze. Okay, so this is the equation we derived. Lots of it are rather conventional, because by having a stochastic equation, you can derive the Fokker-Planck version of that. So from the extension part of this, which is these things, you have that, okay, you have a convection, which is V gradient x of the density, plus the gradient in velocity space of the forces, which are here, oops, sorry, plus the effect of the noise. And then the new terms that we added were the tip branching term, which is more or less reasonable. This is proportional to the probability of branching that we showed before, and the new term which is the anastomosis, okay? So more or less the idea is for this term is that it's proportional to the density at time t, and now if you think of this process, so at this point the active tip that was here at time t was there at an earlier time. So it's reasonable that the anastomosis term should be proportional to the probability at time t of this one and the probability of the earlier time of that one. And if you sum over all of them, you get this integral, which is essentially like a time density of occupation time. So it's a average time in which elementary point at the phase space xv is occupied. Okay. All right. So the equation for the angiogenic factor is just a diffusion equation, and this term is just the consumption of the chemicals by the advancing tip. Okay. This is a result of the simulation. So these are two-dimensional example. You have like a long primary vessel here at the x equals 0, the y-axis. Here this is a source of the angiogenic factor, which is also elongated, and this is some kind of Gaussian profile initially. And you can see that as it moves, it branches, and also when the tips arrive to an existing vessel, it just stops. So this is the anastomosis. Okay. So we wanted to understand this mathematically, and okay. So this is how to derive this thing. First idea we had was like in the works about deriving kinetic theory for gases. Okay, so you imagine that the particles are many, and then use the law of large numbers. And this thing works if the system is self-averaging. Therefore, one trajectory is the same thing as the average. So, you know, the usual way would be define these densities with some large number n that is representative of the number of tips. Then we would get the equations for the density like the one I showed. Okay, if we wanted to prove rigorously things, you would prove that the solutions exist and are unique, and they depend continuously on the initial conditions, the boundary condition, which was done by Carpi and collaborators, and then you would do that. And okay, so that's all right, but turns out it's all wrong in some sense, okay? Because if you look at this, it's not true that there are many particles, because the anastomosis, it's true that you create a lot of them by branching, but the anastomosis kills most of them. So you never have more than 100, say, in the simulations we carried out. So what do you do with that? Well, then we thought that since Gibbs got away with thinking of ensemble averages of identical replicas of the same system, we should try something like that. Okay, so we enter n replicas of the same stochastic process. We did n simulations with very large n, and then we got the ensemble average of those things. And sure enough, turns out that this new concept obeys exactly the same PDE as the other one, which is good for people who prove theorems about that. Okay, so this is the definition. You just define some density. These are like regularized Gaussians with some variances sigma x and sigma b squared. And we assume that these things converge to some smooth functions, obeys the PDE. This is just the integral of that one with respect to velocities. Okay, and then we simulated this PDE, and we also simulated the ensemble average of 400 replicas, which is enough. So we were increasing the number until we got the same result by adding a few more. And you see that what the tips are doing, the active tips are just moving like a patch from 0 to 1. And when you look at the section over the x-axis of this thing, you know, it resembles something like a soliton, turns out. And it is a soliton. Okay, these are details of how you fit the deterministic and the stochastic simulations. Essentially, you fit it in the interval where this patch is fully created and where it's arriving to the tumor, so to speak. So in this part, we fit that anastomosic coefficient so that the two do the same thing, the stochastic and deterministic equation. And this is a comparison of stochastic ensemble averages and deterministic. So it worked pretty well. Now, what about this soliton? Can we describe it better? So this is the asymptotic part, in a way, of the talk. Well, we were able to derive by some asymptotics using that the friction was large. It was 5, but for us, 1/5 was infinity, so we did some kind of Chapman-Enskog expansion of the deterministic equation, and we got this. This is equivalent more or less to dropping the inertia, which everybody would do with cells. And the only thing it does is renormalizes this branching coefficient. Okay, so next thing, it turns out that you can find an exact solution for this equation. You drop the diffusion, and you think that this f, mu are constant. Okay, so you get something that looks like the KdV soliton, the hyperbolic secant square, only it has two parameters. One is the velocity, c, and this k that more or less gives you the size of this soliton. Of course, all of this is not really true, because the tap is varying with time, the diffusion is not really 0, and so on. So what we thought to do another perturbation would be, okay, we think that this k and this c and the position of the soliton are slowly varying quantities, and then we find equations for them, which we may call, because of traditional reasons, collective coordinate equations. Okay. So I'm not going to show them. They involve the spatial average at a particular point of the soliton. And you can reconstruct the density using the soliton, which compares pretty well with the other one. Some is ensemble average, the other was deterministic. A surprise is that if you compare the instantaneous position of the maximum of the density of active tips for any replica, it surprisingly for us, it follows the trajectory of the soliton determined by these ensemble averages. Why does it do that? Who knows? I mean, we don't know yet. Okay, so we think this process that I presented here could be a blueprint for studying other angiogenesis models. For instance, a lot of models in the literature use, instead of Ito equations, reinforced random walks or something like that. Even the microscopic models use Monte Carlo dynamics, and all of these things have some limit that go to Fokker-Planck, Langevin stochastic equations. So we think that it might be possible to pull out all of this methodology for such cases. The role of the equilibrium in conventional Fokker-Planck equation, like a stable stationary solution, we think that is played here by this soliton, which is stable, but we don't know how to prove it yet. Okay, and eventually you can control the motion of the soliton by just these collective coordinates. So we thought that maybe if we see what the effect of these drugs or haptotaxis is on the soliton, we may be able to use that to find a simple control of the process. Okay, well, thank you.
Question?
Yes, as you already mentioned, angiogenesis is extremely important for tumor growth.
Right.
And again, if you could elaborate on the last comment, because I mean, what is really the impact of this work on possible approaches to arrest this growth?
Well,
I mean, you mentioned a couple of words at the end, but maybe
right,
you can elaborate more.
yeah, I mean, this work is ongoing, so I mean, it's not finished at all. So the idea is, by using this model, which may be made more realistic, you can, there are models in the literature that tell you what is the effect of adding drugs, for instance, on the restraining the branching process, or you know, kind of things like that. So you can add that to the model. You can still compute by this process sample averages whatnot, the soliton. It turns out all of these processes, they just affect the collective coordinate equations, just the position, the velocity, and the size of the soliton, maybe the angle with which it moves. So we think that by, since for reasons which we do not understand yet, the replicas like to follow the path of this soliton, if you control that path and can restrain it, we hope that that restrains the growth of this angiogenic network. That's the point.
Just to follow on that, I mean, basically there are sort of two sort of mechanisms which the anti-drugs, genesis drugs are trying to do. One is to try and starve the tumor, that is to prevent the growth of the tumor angiogenic factor attracting the branching
Right.
of the blood vessels. And the other one is to attack, which is what chemotherapy essentially
Right.
is, to try and attack the actual stop the blood vessels growing themselves. And they're both thwarted with huge problems, because even you try and starve the tumor, it says and it switches onto other mechanisms. But I think something that would be very interesting is to look at this, and not many people have done this, is actually angiogenesis is a very natural thing, not just in connection with cancer. And it'd be very interesting to look at the angiogenesis with respect to embryology, because that is absolutely really fascinating. That would explain some of the things that's going on in the rat eye.
That's right.
I think that would be really nice to think.
Yeah, there are all kinds of things that people have been doing lately, like pruning and whatnot, but we can talk later about that.
Thank you very much.